In section 2 of chapter 12, we're going to be continuing our exploration with conic sections, except now we're kind of starting to get into the meat and potatoes of this stuff. We're going to be going over the parabola. Now I know you probably thought, we've done parabolas before. I know how to graph parabolas. I know. Well, I'm here to tell you that you don't know, because there's been two critical pieces of information from parabolas that we've kind of been withholding from you as educators. There's two critical kind of graphical features that you haven't dealt with before, which strangely enough is from the formal definition of what a parabola is. So let's kind of dive into this. All right, so we know a parabola. Parabola is formed when we have two cones pointed towards each other and we take a diagonal slice that forms a parabola. I'm going to start with the stuff we know and maybe extend that a little bit towards something that's you know, but you may not know that you know. First, let's start with bread and butter. What do we know for certain? Which is the graphing form of a parabola is y is equal to a times the quantity of x minus our h value, quantity, plus our k value. And from that we can tell the vertex. The vertex is a coordinate h comma k. So it's whatever the h value is, comma whatever the k value is. And then we also know the axis of symmetry is, that's actually going to be an equation because it's a vertical line. It's x equals the h value. And there's other stuff like the a value tells us stretch and compression factor and yada, yada, yada. And it might look, I have a little graph off to the side, it might look something like, I don't know, something like this, where the h value tells you how far left and right you are. The k value tells you how far up and down you are. With those two pieces of information, you get the vertex. And there's also an axis symmetry, which we mark with kind of like a dotted line or a dashed line. And it always goes through the vertex. Awesome. This is stuff we've done plenty of times before. But there is another version that we haven't dealt with too much, which is sleeping parabolas, parabolas that are on their side. What happens if I don't want a parabola that is like a U facing up or down? What happens if I want it to be a U shape facing left or right? Well, all we got to do is change the input and output variables. What I mean is, instead of a y equals equation, I want x equals a times the quantity of y minus, and here's where things get a little bit more spicy, k quantity squared, and I forgot the square on the first one, plus your h value. So notice x and y swapped, so of course h and k also have to swap. But the vertex is still the same place. Vertex is still going to be a coordinate, and it's still going to be h comma k. That doesn't change. But axis of symmetry is now going to be pointing left and right, so it is still going to be an equation, but now it's going to be a y equals, and it's going to be equal to the k value, because this is going to be a graph that looks, I don't know, something like this. So h is still how far we move left and right, k is still how far we move up and down. That's still going to produce a vertex. But now the axis symmetry is going left and right, and that requires an equation that is y equals, because this is a line that has a constant height. The height doesn't change, which means it's just y equals whatever the constant of that height is. All right, this is stuff we've done before. Maybe the second step is a little bit of a stretch, but I figure we can bridge that gap. But what's new? What's new? Well, let's start off with the graphing feature. If we have a quadratic that looks something like this. All right, so we have the h value, we have the k value, that gives us the vertex, but it also gives us the what's called the axis of symmetry. Awesome, it's fine. However, there are two other critical pieces of information that are really extremely important that we have yet to go over. That is the focus, which we mark as kind of like an X, and it's on the inside of the parabola. It's a very special location, which we'll go over in a minute. And then there's also something that's called the directrix. And the directrix is equally as important. So this is called the focus. And then the orange dotted line is called the directrix. Directrix. And most importantly, for this is that the distance between the vertex and the focus, whatever that distance is, that is going to be the same as the distance from the vertex to the directrix. So this distance and this distance are the same. So whatever this distance is going to be equal to this distance. Now, before I go into how to actually find that value, which is called the focal length, I'm also going to show you visually what it looks like if the parabola is horizontal. So here's a horizontal parabola. Again, the h value is how far you move left or right to find the vertex. The k value is how far you move vertically, up or down to find the vertex. The big key difference here is that now we have an axis of symmetry that is horizontal, because the parabola is horizontal. And what that means is that the focus is going to be left or right of the vertex, and then the directrix is no longer going to be a horizontal dotted line, it's going to be a vertical dotted line. And this distance, of course, is equal to this distance. That is called the focal length. All right, so how the heck do we find the focal length? Well, the focal length, which oddly enough is P, is going to be equal to, and hopefully in a second you'll see why I labeled these red, 1 over 4 times the a value. That's right, we need the a value, the number that's in front of the parentheses. Now remember, if there is no number written here, we presume it to be a 1. So that is going to dictate in the value of the formula 1 over 4a, what the focal length will be, p, and that is the distance that we were talking about. These distances are p units away from the vertex. So again, let's just use the vertical one as an example. Let's say I did an equation, p is 2. That means once I found my vertex, I would go up 2 units to find my focus, and I'd go down 2 units to find where my directrix is. If my p-value for this one was, let's say it was 3, then once I found my vertex, I would go right 3 units to find my focal point, and I'd go left 3 units to find my directrix. We're going to do some examples. But before we do examples, I really love parabolas, and now that we understand what the focal point is and the directrix, because now we can actually get the formal definition of a parabola, but also see some of the really cool applications of parabolas. First, though, let's talk about the formal definition. If you look up a parabola on Google, on a formal math textbook, this is what it's going to say. The formal definition of a parabola is the set of all points, coordinates, in a plane, so an xy plane, which are an equal distance away from a given point and a given line. What the heck does that mean? Well, that means if you start off with one random point and you start off with a line, all of the coordinates on the parabola are just going to be equidistant from the directrix and the focus. So all of those coordinates are equidistant from that point, the focus, and the line, the directrix. The midpoint is the vertex. So the parabola literally came from a mathematician saying, hey, let's pick a random point on a plane, an xy plane, and a random line in any direction. So it doesn't have to be horizontal, it doesn't even have to be vertical, it can be diagonal. But any line that you want, a point and a line, where the point is not on the line, if you try and draw all the coordinates that are equidistant from that point and that closest part of that line, that's where you're going to get a parabola from. All right, awesome. Mathematicians got bored, came up with a couple rules, and they created this shape. And now Algebra 2 students are stuck suffering doing these problems. Why the heck is this useful? Because from that great thought experiment came a lot of technology that we use today. So, how is the focus and directrix useful in the real world? So I have a little GIF down here that is a blue dot that represents the focus. Now we're not going to talk about the directrix too much, but you can use that when you're starting to talk about lenses that are in the shape of parabolas. But let's just say you have a dot right here, right at the focus. And what we're about to do is we're about to shoot out rays. Rays are straight lines. Like imagine there was like a little light source right here, and it's giving light off in all directions equally. Well, something really, really interesting happens to all of those rays that extend from that focal point. They all reflect off of the parabola and then redirect perpendicular to the direction of the directrix. Again, might seem a little bit like, all right, cool, why is that useful? It's because this is how flashlights work. A flashlight is literally a parabolic shape with a light source inside of it, and we are trying to redirect all the light that is coming from that single light bulb into a single direction, a single line. Now that's a great visual representation of how this works, but this also works in reverse. If you have rays that are intersecting with the parabola, you can have them redirect at this central focal point. And that's actually a lot more interesting because that's how other bits of technology that we use more frequently operate. Things like satellites. A satellite is literally getting all of the signals coming at it, hitting the dome of the parabolic dish, and then redirecting them at the receiver, which is at the focal point. Now there's a bunch of other applications as well. We can use them to blast kidney stones. You can use them for bridges. You can use them for, again, like I said, you can use them for flashlights. And you can also use them for what is called an Archimedes death ray, where it's utilizing the sunlight to burn ships at a distance. But let's start talking about some more mathematically oriented operations, shall we? So there are generally two subtypes of problems that I can throw at you when dealing with parabolas. I can either give you information about where the focus and the vertex is and then have you figure out the equation and graph from there, or I can give you an unfactored version of the problem like we're doing problem number 3 and actually have you find the vertex form and then with that find the vertex, the focus, the directrix, and graph that shape. So let's jump into this, shall we? Problem number 1. We have a focus at 1, 5. Remember, focus is written with an X. So I'm going to go right 1, up 5. There's the focus. I have a vertex at 1, 3. Right 1, up 1, 2, 3. So here's my vertex. And one of the things that we know is that the distance from the vertex to the focus, which is a distance of 2 in this case, that's the same as the distance from the vertex to the directrix. If I go down 2, this is where my directrix is going to be. So I now also know where the directrix is. So we've got graphically 3 really critical pieces of information, but I can't just draw a parabola and say I'm done, because that would just not work. I want some detail. And I can't just presume that I'm going to go right 1, up 1, right 2, up 1, 2, 3, 4. I can't presume that there's no stretch or compression factor either. I need to get some more detail. So we can't just jump straight to graphing the parabola and being done. We actually need to generate the equation. Since we have the vertex, we already know a good bit about how to write the equation for this. The equation thus far is y is equal to a, which we don't know, times the quantity of x minus 1, so we shifted right 1, quantity squared, plus 3. Because again, that'll shift us right 1 and up 3, which is where the vertex is at. But we do not know the a value. We do not know the vertical stretch and compression factor. But luckily, they tell us the focus. They tell us the focus is 1, 5. That's a jump of 2. So I know that if I utilize my formula to find the focus, which is p is equal to 1 over 4 times the a value, I can use that formula to actually find my a value if I know the p value. So I just found out the p value is 2 because in order to go from the vertex of having a y value 3 to the focus's y value 5, I need to jump 2 units. I know this is going to be 2 is equal to 1 over 4a. I'm going to multiply a to the other side. That way I don't have a in the denominator anymore. And that'll get me 2a is equal to 1 over 4. Then I'm going to divide both sides by 2, which is the same thing as multiplying by 1/2. And then that'll finally get me my a value, which is equal to 1/8. And now I can write the equation, which is not going to be y equals a. It's going to be y equals 1 over 8 times the quantity of x minus 1 quantity squared plus 3. And this is my equation to the vertex. If I wanted to get a more detailed graph, I could, but I'm just going to kind of leave it as kind of a sketch. In problem number 2, same thing. Our focus is at 0, -2. That means we're just going to go down 2 and mark it for our focus. Our vertex is 3, -2, so we're going to go right 1, 2, 3, and then down 2. There's our vertex. Well, if the focus is 3 units to the left of my dot, my vertex, then the directrix will be 1, 2, 3 units to the right. Notice that this is going to be a vertical dotted line. The problem is going to look something like this-ish. But let's get the actual equation, shall we? So first, we already know that the formula is going to be x equals, because it's now going to be facing left and right. I also know that my a value is going to be negative, but I don't know what the a value is. But I do know it's going to be y plus 2 squared plus 3, because I went down 2, up 3, up 3. Again, that's what makes these a little bit more difficult, is when they're x equals equations, basically parabolas that open left and right. Then the number inside of the parentheses is next to the y value, which indicates that this number affects our y value of the coordinate, not the x value. So it's the same process, same thinking, it just looks a little different because it's from a different perspective. To find the a value, again, we're going to need the formula. P is equal to 1 over 4a. That's how we find the focal length. But in this case, it's going to be, our a value is 3 is equal to 1 over 4a. And do some matho-magics. Multiply a to the other side, then multiply both sides by 1/3. We're going to get a is equal to 1/12. Now it is negative because we're pointing left. If you wanted to, you could say that to kind of get the negative, which I knew was negative because we're going in the negative direction. But if you wanted to actually have your math kind of support that, technically the p-value is -3, which would make this a -1/12 if you wanted to have it match up. But there are some texts that say that the focal length, the p-value, should always be positive. So depends on who you're learning this from. They might say one way or the other. But our formula is x equals -1 over 12 times the quantity of y plus 2 quantity squared plus 3. There is the equation. So the first two problems kind of give you the focus, they give you the vertex, and then we just utilize the formula to find the focal length to determine the equation of the quadratic. Problem number 3, a little bit different. Now it's all multiplied out, and we're actually going to need to figure out what the equation is in a different way, because we don't know what the vertex or the focus or the directrix, we don't know any of that stuff. Now the first thing I want to point out is that it has a y to the second power. What that indicates to me is this is actually going to be a quadratic that is going left or right. It's going to be one of those things. Because most quadratics that we're used to have an x to the second power. So first step is I actually need to get the x by itself on one side of the equal sign. So I'm going to add the 4x to the other side. And that'll leave me with y squared plus 6y plus 1 is equal to 4x. Next, I'm going to complete the square. I'm going to complete the square with these two pieces. That means I'm going to get y squared, a positive 3y, a positive 3y. That means I need a y plus 3 and a y plus 3. That means the piece that I am missing is a plus 9. So in my equation, I am going to have y squared plus 6y plus 9 plus 1 minus 9 is equal to 4x. I can utilize these first 3 points or parts to actually write the quantity that's being squared. That is y plus 3 squared. Positive 1 and negative 9 get me a negative 8, and that is equal to 4x. We're nearly there. I just need to divide everything by 4. I'm actually going to put the x on the left side because that's just how I like my output variables is on the left. X equals, instead of the quantity y plus 3 quantity squared all divided by 4, I'm going to write it as 1/4 quantity of, not x, y plus 3 quantity squared minus 2. And now I have my equation. So we're going to be shifted down 3 and left 2. There's our vertex. I also know that it is going to be facing upwards, something like this, because the a value is positive, but now I need to find my focal length. I need to find the p value. P is going to be equal to 1 over 4a. That means that p is going to be equal to 1 over 4 times 1/4, because that is our a value. Therefore, p is going to be equal to 1 over 1, which is equal to 1. That is my p value, that's my focal length, which means if I go up 1, that'll be where the focus is. If I go down 1, that is where the directrix is. And these are the 2 types of problems that you're expected to understand how to accomplish. What happens if I just give you the focus and directrix? Sorry, the focus and the vertex. Can you determine the equation and give me a rough sketch of the graph with the proper location for the vertex, focus, and directrix? Or if I give you a completely multiplied out quadratic like I do in number 3, can you derive the vertex form and then from that determine what the focal length is, which will determine a sketch for the parabola with the vertex, the focus, and the directrix?